Okay, so the first question is for Dr. Nichols. So if I had an EKG done several years before my PD diagnosis, would my test be useful, thrown into the search for biomarkers in heartbeat irregularities evaluation?
It kind of depends on, well, first of all, right now we're just experimenting on this in a research way, and we're trying to answer that same question, actually. We're trying to see how much information we need from an EKG to be able to look at, the particular kinds of changes that are another one of those factors that might predict risk or identify what we call prodromal PD. So the traditional way of looking at it has involved an electronic digital strip, and for a long period of time, so at least 5 or 10 minutes continuous. So most people actually don't have that available in their background. But we're actually just starting to see if you can use smaller little bits of the EKG and come up with useful information. So the answer at this point is probably we couldn't use it, but maybe we'll figure out a method that would be useful in the future.
How is the research proceeding with the molecular scissors? There was a grant issued 1 to 2 years ago.
Yeah, I think I said a little bit on the last slide on the molecular scissors. So this is a grant that is together with Sangamo Biosciences, and the goal of the grant was to actually correct one of the LRRK2 mutations. It's the G2019S mutation. It's the most common mutation in Parkinson's disease. And I have to say, yes, we were successful with this method, and we have generated multiple cell lines that have now the correct sequence. We also have a set that went through the whole process but maintained the mutation, so we use those as controls. And we also have developed some lines that actually knocked out the LRRK2 genes. So they, the method introduced short deletions that would then result in a functional knockout. So I have to say, this has been a very successful collaboration with Sangamo Biosciences. We've been into this grant a year and a half, and we have another a year and a half until it's completed. The plan is now for the next year and a half to actually introduce the LRRK2 G2S mutation into a healthy stem cell line. So that's the goal for the next year.
What is the relationship of adderall to Parkinson's? What research is being done on this? Please explain odds ratio and confidence interval.
Okay. So we were just talking about this a little bit. We're not sure about the relationship, but there's some suggestion that there may be an increased risk, and a little bit of evidence from an animal model as well. The idea of odds ratio is you're looking at a comparison between people who are have a certain characteristic compared to people who don't, and you're trying to figure out what is their chance of getting disease. So that's basically the idea, and so it's the odds, like odds if you're gambling, between people who are exposed and people who are not exposed of developing Parkinson's disease. So that's what the ratio is. And what we're, confidence intervals are just a way of saying how likely is this answer to be true, right? So it's a way of putting sort of a numerical boundary around what your outcome is and saying, you know, the upper limit of what we believe this number could really be is this, and the lower limit of what we believe this number could really be is that. And here's the number we came up with. So it gives you an idea of how wrong you can be. Because when we're doing our estimates, we're looking at usually relatively small numbers of people, relatively small populations. So just by chance, you could come up with something that looks really important, and maybe it isn't important at all, right? So the other thing that we do to try to get around that is we try to do what we call replicate. So we try to look in multiple populations and ask the same question to see if we come up with a similar answer. So many of the things we're looking at in our epidemiology studies are things we have to repeat over and over again in other populations to be sure that they're true. That's true in the lab too. All the lab people will say they do replicates, but they can control things much better than we do because we're just observing and collecting information from people about stuff that already is. We're not giving them an insult and then observing it and only changing one thing at a time. So we have to be especially conservative when we make, sort of come up with ideas based on our observations in humans. On the other hand, it's humans who have the disease, so we have to look there.
How do your labs collaborate with each other to further PD research?
For example, my lab, or we have a grant together with the Nichols lab. So, for example, we have made induced pluripotent stem cell lines from patients with LRRK2 mutations. And of course, those induced pluripotent stem cells, or then the differentiated neurons, are also of interest for Dr. Nichols and his research in LRRK2. So he's using those lines and then looking at specific mechanisms he's interested in.
Okay. So I'll just take a more kind of a big general overview of how we work together. So the stuff I was telling you about what we observe in human populations and how that gives us clues about the cause of disease or clues about what makes the disease progress more slowly or more rapidly, those are just observations and associations, and the only way we can really figure them out, even if we replicate them in multiple populations, is for the people in the laboratory to then take those clues and model them in the laboratory and try to figure it out. So, some of our big mysteries are things like smoking and the inverse association between smoking and risk of Parkinson's. Well, we need people in the lab to try to look at that and figure out, does that have an effect in an animal model of disease? Can we figure out the biologic underpinnings of that? So there's a lot of back and forth about those kinds of things. Similarly, looking at genetics and genetic forms of disease, and then going back to the laboratory and saying, can you understand, like if we are good developing cells or developing models of that, to come up with mechanisms, how do these gene mutations affect the cell? And then that leads to ideas about treatment, and then treatments get tested in humans, and we kind of are always going back and forth and cycling back and forth among ourselves to come up with better answers.
Yeah, like Birgit said, we do have some collaborative grants together, and these are formal ways that our collaborations are recognized. But every single day, we have independent laboratories that are codependent on each other's abilities and expertise. I mean, I've published papers on mouse, genetic models of certain diseases, but that's not my expertise. It's Yang Ping's, and so. One of the things this allows us to do is to not stovepipe our abilities, but to interweave them in a way that is really beneficial and synergistic. So if I have certain observations that I think can be tested in Birgit's cell models, then it's very easy for us to go across the hall and say, hey, we had these new ideas. It was based off of some observation of Carly's, and then we tested it in our models. Now can we put it in your stem cell models? Or in Ping, now we can test this, we see this effect in she said in cell culture, so in petri dishes. I have my own particular models of disease that we try to use to elucidate these particular mechanisms of disease onset. And so when we find out a mechanism at one level, we can take it to the next level, maybe to an animal model or a stem cell model of disease. And so, like I say, these are recognized through formal things like grants that's been awarded to us, but also just in the fact that we can walk across the hall and say, hey, Carly, what do you think about this? Or Yang Ping, this is my new idea. So this is a place where, and it's not even restricted to the people in the basic research areas. I constantly learn from people in the clinic about, one, that everybody's PD is different, and every patient is their own situation that has to be dealt with. And so understanding that this is what we call pleomorphic, or not the same kind of disease for everybody, that it's really beneficial in how we ask our questions and when we say, what's the best next step? So I would say, in addition to the formal things, it's the informal abilities that, just our proximity make us a better place to do science.
Outside of university setting, how common or how rare is the Parkinsons Institute model? And is that a good thing, or would we be better connected with, 7,000 doctors at Stanford or something?
Well, for me, I mean, the particular things that I do could most likely be accomplished in any university setting. I would say that, unlike a university, we have these elements integrated because, typically in universities, there's a building where science happens. Whatever that magic is, and then there's a building where the medicine happens, and those are two separate entities. Here, I see Dr. Tanner and Dr. Shuley every day. I mean, they have MDs. I have a PhD. I mean, this is a rare occurrence, and I would say it's one of a kind.
Yeah, I think there's no other place in the world exactly like this. Surprisingly, in universities, while they may have all the pieces, they don't necessarily connect. And in fact, it's very common for, this researcher over here and that researcher over there, even if they're both basic science researchers, to find out there's somebody else in their university doing something that's very complementary, sure, just by happenstance. In fact, there isn't a good way in a big university most of the time for these kinds of things to be organized. So the fact that this place was founded, I've been here for a really long time. I came here because of the model and the idea that the best way to address questions about people with Parkinson's disease was through this constant interchange between people who are doing patient care, people who are doing clinical research, including clinical therapeutics and epidemiology, and then people in the laboratory. And that's the most efficient way to get where you want to go, which is to be able to really make a big impact in the disease. So I don't think there's another place in the world exactly like this, actually.
I only want to add the fact that I think this is a very special place to do this type of translational science, as we show here, that we can use human-derived samples, blood samples, skin samples, to do this research. Very unique. I mean, there are other large universities and large consortia that try to do similar work, but they have to work with 10 or more centers to get the number of patients that we have here from our clinic. So that is something very, very special, and I think that's the reason why we all work here and think this is a very, very unique place, the Parkinson's Institute.
Now, I've read that because of the increase of chemicals in the environment and the aging of the population, that Parkinson's is increasing. Can you comment about that?
So the absolute number of people with Parkinson's is going to increase because more people are living to an age at risk, and Parkinson's is a late life disorder. So what we call prevalence, the number of people at a given point in time with Parkinson's, will be greater in the US and in lots of developing countries. In fact, we think it's probably going to double by 2030 compared to 2005. So really big difference because of the aging of the population. What we don't know is the first point you made. We don't really know if the incidence, so the proportion of new cases is increasing or not, because no way to measure that. So the pilot project for the registry that we're doing was set up exactly to try to address that question. Are there really more and more people developing disease because of things in the environment, or are there just more people because the population is older?
What about the diagnosis? Since this is very difficult to diagnose, is there differences in how that's been applied, which may mean the numbers from one year may not match on the same scale?
Yeah, so the question is, because it's hard to diagnose Parkinson's, it's very, very much dependent on who's making the diagnosis to a certain extent. Does that account for some of the questions or the uncertainty? It certainly adds to the uncertainty. And in the studies that I do, that I report, we go to great pains to try to be sure that people meet what we call, established diagnostic criteria. So certain criteria that make it more likely that somebody with certain symptoms really ends up with the typical pathology that is what we call Parkinson's disease. We know if you look in populations where it's mostly primary care physicians making the diagnosis, about 10 or 15% of the people called Parkinson's will have a different tremor disorder, for example, something called essential tremor familial tremor. So who makes the diagnosis does matter, but even taking all of that into account, we know there'll be more people as the population ages. We just don't know if the proportion will also change.
You listed a couple of chemicals for pesticides. Has anybody created a list of actual products by name that include these chemicals that could be shown to people that says stay away from them or whatever?
Yeah, I don't know if there's a list exactly like that, and you know, we're talking about chemical names, and there are lots and lots and lots of products out there with sort of different names. So when we do our research, we try to develop sort of population and time period specific lists of brand names of pesticides, for example, to show to people. I'm not sure if there's a list like that. I'll also say that these are things that we're looking at that may be associated with causes of Parkinson's. We don't know what their effect is on somebody who's had PD already diagnosed, so kind of makes sense. Maybe you want to stay away from them, but nobody's really been able to look at that yet.
Well, let's give another round of applause to these scientists.